All right. Okay. So this this figure is basically just an illustration. Okay. So I look at the two. This is the Wisconsin breast cancer data, and I took these two variables: concave points mean and radius worst. Right. So so I just plotted them. So they look like that. So if you perform support vector machine, right, using the Kern lab, then you can actually estimate the decision boundary, all right? And then these are your margins, right? The upper and lower margins, okay? And this can be, so these lines are drawn from theory, yeah? So based on theory. So you can see that the classification is actually not too bad, all right? You put a straight line through this, you kind of like get some decent results. Okay. Then let me share the other one. Okay, so kernel. Okay. New share. Okay, this one, right? So can you see this figure?
Yes.
Okay. So this figures. So this decision. So this figures, right? You can see this region, isn't it? You can see these regions. These regions are actually plotted using the plot decision boundary function that's attached as given to you as a separate R file. Okay, so you just basically need to load it so that you can use that function. You see that it's very interesting because it basically what it does is that after it has estimated the parameters, yeah, of the SVM, it basically just does prediction. All right, there's a very nice function in R called predict. So basically, you just give the model, and then you give the data that you want to predict. So it will make the prediction. Yeah. So what it does is that it basically gives all these values. It takes a grid. Yeah. So over the grid of these values, it treats it as a sample, and then it basically predicts. Okay. So for me, I think that is a very smart way of kind of like coloring the region. Yeah. Okay. So basically, you can see that these are the grids, and so basically there's a result here. You basically generate pairs of x and y values in this space, and then you basically use the model to predict. So of course, in this region, if you have a decision boundary here, the values that are at this side, they'll be predicted as blue, right? So then you color it blue, and then when you have quite a dense coverage of points in this region, then it becomes kind of like it looks shaded, right? So it's very nice. And then at this edge here, right? At this edge here, you basically color them as black. Okay, so you will be able to show this line here. Okay, so you can see the results. So you have the linear kernel C equals to 1, and then this is C equals to 100. So not much difference. Yeah. In this case, both C is your cost parameter. So in this case, the linear line doesn't change that much. All right. So they are about the same. Now, if you use the polynomial kernel, yeah, the polynomial kernel can have, you can specify the degree. You can specify as a degree 2, degree 3, and so on and so forth. Right? 2 is quadratic. 3 is cubic, and so on. Right? So you can see very interestingly, if you set it as 2, your decision boundary is basically kind of like an ellipse here. It's elliptic. Of course, it makes mistakes in this region. Yeah, all right. If it's a degree 3, it looks like there is a curve like this over here. Okay. So let me move on to the next figure. So, okay. So can you see this figure? This is the Gaussian kernel. All right, can you see the Gaussian kernel?
Yeah.
Yep.
So basically, for your Gaussian kernel, there's this parameter called gamma. Okay. So the gamma is, it kind of like controls the complexity of your Gaussian kernel. So if you set it to be very low, it basically is close to linear. All right. You can see that this line is actually kind of approximately linear. The moment you start to increase it, it becomes curved. All right. So for this one, you can see the curvature, and this one, it becomes some curve like this, gamma 1. And when you set your gamma to be 10, right, it becomes like this. Okay, it kind of like is looks kind of like some kind of a more complicated shape, right? So then you know that if you use the Gaussian kernel, you set gamma to be large, you will get some decision boundary that is what do you call that, with a very
Overfitting?
Sorry?
Will it be overfit?
Yes, they will come to that topic later. Yeah, but when you set it to be high, right, it will fit the decision boundary will kind of like look very good for your training data. But we will see later that doing this actually is quite harmful to your machine learning algorithm. Yeah, you shouldn't set parameters that give you fantastic results. So I explain that later, right? But you can see here, the curve becomes kind of like it fits the data too well. Okay, and when you see this, you have to be careful. So when somebody shows you machine learning results that are too good to be true, you should start to check all these model parameters, right? Whether certain complexity parameters were set to some value where it is modeling, basically it's modeling noise. It's no longer modeling the main features in the data, but it's also capturing all the noise that is inherent in your training data. Okay, so you have to be careful about that. So this is your Gaussian kernel, yeah. Okay, then you have, so this is the sigmoid okay, oops, resume share. Okay, so this is the sigmoid kernel function. This sigmoid kernel function is the same as the hyperbolic tangent, yeah, TANH kernel function. All right. So again, it also has several parameters, gamma, 0.115 and 10. I just use the same as I use for the Gaussian. You can see that when it is small, when gamma is small, then you basically have something that's close to linear. But when the gamma becomes 1, you can see this, yeah. This decision boundary can actually go to the other side. Okay, so you can see that it defines one section here, one section here. So if you really have data that behaves like this, then your sigmoid kernel function would be fantastic, right? For example, in your real data, your rate, you do actually have some stuff in this region, right? But unfortunately, it's not true. So in this case, for larger gamma, basically this region just kind of like becomes tapered. All right, it becomes kind of like a taper. So you can see that, of course, it's making mistakes in this region. Yeah. Okay. So so therefore, if you apply the sigmoid kernel function, you are not going to be doing well if your gamma parameter is actually quite large. Okay. All right. Okay. So once we have that, we can look at the results. Let me see. Comparison. Okay. Performance. Okay. Can you see my text file?
Yes. Yes.
Okay. So for simplicity, I basically just consider three metrics. So these are the sensitivity, specificity, and accuracy. By the way, these quantities are conditional probabilities. Yeah. So so later I'm just going to quickly relate them to conditional probabilities. But over here, maybe you just accept them as metrics for the time being. So we have sensitivity. Basically, sensitivity of a classifier means that if I give the classifier a class label that is known to be of interest, let's say plus, right? Let's say plus is your label of interest. If I give you something that has a label plus, what is the chance that your what is the probability that your classifier will actually declare it as being plus? All right, so that's sensitivity. So basically, sensitivity is if I give you something that I'm interested in detecting, what's the chance of me detecting it, right? If you look at this kind of diagnostics for COVID, right? Now you have all these methods. If your diagnostic has a high sensitivity, that means if somebody has COVID, then your test result will show as positive. Okay, so that kind of test we say that is very sensitive. Okay. On the other hand, specificity is if I give you some class label that is not your main focus, right? Let's say the negative class label. What is the probability that you declare it as negative? Okay, so in terms of if you look at the COVID context, that means if I give you someone who is normal, yeah, who doesn't have COVID, what is the chance that the test result will be negative? Okay, so that's specificity, yeah. Unfortunately, most diagnostic tests, they are not perfect. They will have sensitivity that is maybe just 80% or 70%, right? So if you have a sensitivity of 80%, it means that for every 100 people with COVID, right, you test, yeah, for every 100 person infected with COVID, right, you go and test them, your result will declare about 80 of them to be having positive result, but then another 20 are missed, yeah. Okay, and that's because your test is not sufficiently sensitive, right? And specificity is if your test is very specific, then that means people who don't have the disease, they will be shown a negative result. All right. So of course, ideally, you want the test to be sensitive and specific at the same time. Okay. So it's the same with this kind of machine learning classifiers, right? So when I give you the data, you make a prediction. You can also check these aspects such as sensitivity and specificity, okay? And of course, accuracy is easy to understand. It is just the total number of correct predictions, right, out of the total sample size, okay? Now, accuracy is not very useful if you have unbalanced class ratios. For example, so accuracy is most useful when your class ratio is about balance, yeah? For example, in a binary case, the number of positive cases and negative cases are about the same, yeah? The ratio is about 1:1. Then accuracy would be useful, yeah? Because if you guess randomly, then your chance of being correct will be about 50% in that case. However, if let's say in your data, right, most of the samples belong to one particular class. Let's say your positive class contains in your sample, 95% of your samples are of the positive class, and only 5% of the let's say 95% of the negative class, and only 5% of the positive class, right? And you are interested in the positive class. So with this kind of very unbalanced situation, then you will find that your accuracy is not that useful. Simply because when you have this kind of unbalanced case, right? If you basically just guess with the majority class, let's say no algorithm, your strategy is just everything that comes, just guess it as the majority class. In the previous situation, you will be right 95% of the time. Okay? Don't care. Anything comes in, just declare as being of the negative class. You'll be right 95% of the time. It looks great, right? But then that is pointless because the whole point of your classifier is to detect the positive class, right? That 5%. So in that case, your accuracy is actually not useful, yeah. Okay. And in any case, when you have accuracy estimates, it has to be compared with the baseline accuracy. Okay, your baseline accuracy is basically just the accuracy that you get by simply guessing with the majority class label, right? So for example, if your data contains, let's say 70% of negative class and 30% of positive class, you guess by majority class, that means you guess everything as negative, right? So on average, you will be right about 70% of the time. Yeah, your accuracy will be 70%. Okay, and so if your classifier is useful, right, it should show something that is higher than your 70%, right, the baseline accuracy. Okay, so if you build your classifier, you only get something like 72%, 73%. Well, that's really bad because your baseline is already 70% and you are just squeezing like a few percent out of the data set, right, with so much work. So that is not very clearly not something that you want. Okay, all right. So with this, but in this data set, we have I think the class ratio is actually quite balanced. So it's not too unbalanced. So we can still look at accuracy, right, as a kind of metric. So you can see all these values, yeah. Different SVM models, and there are different performance, okay. And I picked up some of them. I flagged some of them as for your attention, right. The star is the top performing SVM model with respect to training set, okay. The Gaussian with gamma 10. You look at all the metrics, perfect, yeah. Sensitivity of 94.8%, specificity of 94.7%, accuracy close to 95%. Okay, top performing. The second highest accuracy, the simple model. Okay, which one? The linear model with C equals to 100. All right, not bad. With just a straight line, you get sensitivity of 90%, specificity of 95.8%, and accuracy up to close to 94%. And negative is the worst model. The worst model is your polynomial, yeah, your polynomial model. You can see that while the specificity is quite high, close to 96%. Your sensitivity is really low, yeah. Okay, so it's missing out on those important classes that you want to detect. And then the accuracy, as a result, your accuracy is actually not that great, yeah. Okay, so then the rest are those kind of values. Okay, so your polynomial d equals to 3 is not too bad, 74%, but polynomial d equals to 2 is really quite bad, okay, for sensitivity. Okay, now based on this result, right? So how would you choose the model? So if you could pick one model from here to use for your future work, right? Yeah, if you want to pick one of these candidates to test unseen future samples, what do you think? Which ones would you choose? So I want to hear some suggestions from you.
Is this all training metrics? There's no testing metrics over here, right?
Yeah, this is purely just the performance on your training data. So you haven't used the model on some unknown unseen data. What do you think? Which model would you? So okay. Let's say I give you all these models, and then you had the just now you had the benefit of looking at the decision boundaries, right? Yeah. So which one do you think you want to consider for your next future work?
The linear one. Yeah, the linear one, I think. The C, it's a bit hard to choose to C equals to 1 or C equals to 100 because it's like, if I'm not mistaken just now, it's almost like the same. And then probably the easiest one at the moment.
Okay, so let's put down some names here. Screen sharing. So I annotate. Okay, so it's Jake, right? Jake.
Yeah.
You pick which one?
The linear C equals to 1.
You pick this one, huh?
Yeah.
Okay. How about others?
Hello, doctor.
Yeah.
I will choose the linear model with C equals to 100.
You choose this one?
Yeah.
Okay. Okay, how about the rest?
Gaussian gamma equals to 10.
Which one? Gaussian? You want to choose this one? 思路.
Yeah.
Okay. Okay, everyone must choose a candidate. So let's see. In Chun, C equals to 1. Chao Hong C equals to 1. Alia C equals to 1. Cha Chong C equals to 100. Ruby Wing Feng polynomial. D equals to 3. Farah Gaussian gamma equals to 1. Hafiz sigmoid gamma equals to 1. Wei Yao gamma 1. Sorry, Wei Yao is sigmoid gamma 1. C Kim linear 100. Zhang Qianyi linear 100. Kyok Hua sigmoid gamma 0.1. Jeffrey linear, okay. B Wei linear 100. Yu Jing is 1. Anyone else who has not decided? Alex, is Alex here? Alex. Amy, Alex. Amy Gaussian gamma 10. Alex? Which one do you want? Alex, here? For Hannah? Okay, never mind. So we have quite a few choices here. So popular. So which one is popular? These two are popular. But then there are some other differing opinions. Yeah. Okay. Okay. So let's start with the most obvious result here. Okay, the most obvious one is this top performer, right? Okay, So this is so you estimated the data from the training data. Sorry, you estimated the decision boundary from the training data, and then you use that to predict the label for your training data. Yeah. So that means you're basically using the same data to do model parameter estimation and also prediction. Now, you have to be careful with this kind of so one problem with this kind of approach would be the issue of generalizability. Now, when we want to do prediction, right? The key point is this. It has to be highly generalizable. All right, that means not only predicting well for your training sample, but you should have some confidence that it will also do well, yeah, for unseen samples. Okay, so let's look at this part here. Although it fits very well, right? So let's go and look at its decision boundary. Let's go back to check its decision boundary, yeah. Okay. Right. So this is the so is this one, yeah? Annotate. Okay, this one, yeah. Now, if you look at the decision boundary here, this decision boundary here, I believe it is actually modeling. It's actually modeling noise already. Okay. So, for example, if you have future data, right? In fact, if you are only able to use Gaussian methods, right? Of course, this one basically, these two basically this one basically is identical to your linear. So basically you don't have to consider this. So there are these three candidates. Okay. I think, okay, so which one is reasonable? I think this one is okay. This one is okay. There is a slight curvature here, but it's not too bad. Okay, I think this one is still okay. This one I think is over modeling. Right, so it starts to over model already. Right. So just for you to understand over modeling, right? So the example that is commonly used is when you have linear regression. Okay, so you can basically there are many ways to fit a regression line, right? So basically you would fit some line like this. Okay, right? And that's fine, right? Now, of course, when you fit some line like this, you are going to get some errors. Okay, yeah. So these are your errors, right? However, this line is definitely much more generalizable for future samples than, let's say, if you had fitted it with this line. Okay, if you fit a line like this, basically your model, right, explains the data completely because there's no residual, right? So this model will have R squared that is 100%. Okay, The linear model explains so your model here, the piecewise linear. Yeah? So this is basically a piecewise linear. So you just join a linear line between two adjacent points, right? So the piecewise linear model is has an R square of 100%. It explains all the data It explains the data perfectly. Yeah. This kind of model is surely going to fail very badly in a real test sample, right? Your real test sample basically may end up going to places like this. So if you use this curve, so you will maybe do worse than, let's say, a straight line. Okay. So this is a problem of what we call overfitting. You can think of overfitting as studying for exams. Okay. Some people do extremely well in exams. Okay. And the reason why they do very well in these exams may have less to do with their actual ability than overtraining. Like for example, one of the things that encourages overtraining is you do past year questions, and you do past year questions, and the examiners actually kind of like set similar questions like past year questions. In that sense, you will get a lot, if the person overtrains on this kind of past year questions, when you come to the real exam, since it's drawn from the similar kind of samples, right, that the person used to learn. So this person will do very well in the exam, yeah. But this kind of people very likely will do very badly in a more kind of like volatile kind of situation, where you are given maybe questions that are outside of what you are used to. Okay, you may find that these people they might fail very badly. Okay, and then you get some of these guys who actually don't overtrain themselves, right? They look at some of these exam questions past year, yes, but then they also try to kind of like learn things more on a general principle kind of approach, right? And then maybe then they look at questions. They don't just look at questions from the past years, but they look at from a very broad source, yeah, maybe from other countries or whatever. So this kind of people, right, although maybe because they spend their time looking at a more kind of like broad set of exam questions, as a result, they might not do so well when the actual questions that actually tend to be recycled from previous past year questions are given. However, this type of people, they tend to do much better when you have future samples, yeah. Okay, simply because they have looked at a broader set of questions, right, from the field. So the analogy is like this, okay? I find it to be a useful analogy. So over here, I would definitely not consider this model, okay? But I think this one is okay. This one also not really, okay? So I would consider this gamma 0.1 should be not too bad, right? There's a bit of curvature, so approximately linear, fine. So let's go back to mouse. Okay. Share. Oops. New share. Okay. So can you? So I come back here. So I think. Oh, it's all gone already just now. Already cleared. Okay, never mind. As long as you remember what you have chosen. So I think this one is still okay. So so we're not going to use this one, yeah. Also 1 0. Okay, this is okay. This one we don't need to consider this because it's is belong in the might as well just use the linear class. Okay. Just now who chose the Gaussian gamma equals to 0.1? Anyone? Anybody chose this? So the point is there are several I think equally reasonable candidates. Okay, so this is okay. For sigmoid also, I think these two are out already because they have some weird decision boundaries, right, for the rate class. So I think these three are out. But this one still may be okay, not too bad. Sigmoid gamma 0.1, but these two they have the same performance, right? So basically, these two are about the same, yeah. Gaussian gamma 0.1, sigmoid gamma about the same in this case. All right. Yeah.
It seems like exactly the same, right?
Yeah. I mean, like the metric is the same, but the decision boundary is slightly different. I mean, like they are approximately equal, I would say.
Understood.
Their decision boundary not exactly the same, but approximately the same, so it doesn't affect the metrics here, right? Okay, so polynomial 2 definitely out. Okay, I think even on the training set is doing very badly, right? So so it is very unlikely to do well for the future data. Okay, so we're going to get rid of 2, but how about 3? Wing Feng chose this, right? Wing Feng, you chose this polynomial d equals to 3. So it's an unusual choice. So can you maybe just want to get your rationale? What's your rationale?
Actually, I just guess only, and I'm actually looking at the specificity. It's the highest, so I chose that.
Okay, so you're focusing on the specificity.
Yeah.
Okay, so Wing Feng kind of like said he wanted a method that was maybe highly specific. But if you remember the decision boundary, right? I think for the class, I think it went something like this. Okay, so with the red somewhere around here and the bunch of blue somewhere around here. I think this curve here is of doubtful. I think it's just doubtful. Okay, that and this may be just basically just maybe just coincidence for the training set. The point is it's actually doing quite badly on the sensitivity already. Okay, and then there's a kind of like a weird curvature here on this space. So it will not be something that I think it's one of the prime candidates, right? So okay, so this is gone. So we are left with these two. Okay, so these are both linear models. Yeah, I think there are about the same number of people who chose with penalty cost equals to 1 and cost equals to 100. So so basically this is a hard margin. This is a soft margin. I mean, like this is a harder kind of margin. This is a soft margin. Okay, this is a softer margin, right? So if you look at when you set C equals to 100, so it's considered a kind of like a soft margin. Okay, so I think there is really nothing much to separate these two things. Although of course there are some differences, but it's too minor. I would say these two models are more or less the same. Okay. So basically, linear, either C equals to 100 will do. And also you could pick Gaussian gamma 0.1, sigmoid gamma equals to 0.1. Okay, so these are all possible candidates that I think will have pretty good performance on the future samples. So except that if you want simplicity, then perhaps if sometimes model simplicity is important, yeah. So if you want something simple, then maybe just go for the linear C equals to 1, right? The linear models are easier to explain, right? So rather than let's say Gaussian and sigmoid, so these two would be a bit harder because then you would have to invoke the kernel function. Let's say if you imagine after you have built your classifier, you'll try to explain it to someone, yeah? Although all these three candidates, all these four candidates are promising, but generally you would go for simplicity, right? Okay, go for simplicity, and in that case, perhaps going for linear model is best. Okay, with respect to not with respect to performance, because performance, I think all these four will be about the same, but with respect to ease of interpretation, right? So linear model will have an advantage, right? Because people understand linear models better. Okay. So this is my discussion about how to look at how to pick the models, right? Based on the training data. Of course, later we will go a little bit deeper into how exactly we should actually test the performance, right? So the actual way to choose you can actually evaluate the performance of the potential of a classifier by withholding a certain subset of your data as a test sample. Okay, so when we come back, I'm going to talk a bit more about that. Okay. All right. Okay. So it's 7:30 now. So let's take a break until 8 o'clock. Okay, so let's continue. Yeah, welcome back. All right. So now I want to follow up on the. Okay, so before that, maybe just I quickly cover definitions of sensitivity. The following metrics, yeah. Sensitivity, specificity. Then there's something called positive predictive value. PPV. The other is called the negative predictive value, okay? NPV. And of course, you have your accuracy, right? So all these are actually obtained from a classification matrix, right? So your classification matrix, for the case of binary, binary classification, you will have, this is the true class. It is positive, negative. This is a predicted class, right? Okay, predicted using any classifier, right? Okay, so you will have these quantities A, B, C, and D, right? So here you have your column marginal. So, sorry, this is your total. Again, this is your total. This is your total, right? So this is A. This is A plus C. This is B plus D. This is A plus B. This is C plus D. So this is N, right? So N is A plus B plus C plus D. Okay. So when you talk about specificity, when you talk about sensitivity, so it is basically the conditional probability, all right? Okay, so it's a conditional probability that given the true class equals to plus, you predict it as plus, right? So you only look at this column. So therefore you have A out of A plus C, right? And then your specificity is equal to, look at this column. Okay. So be D over B plus D, yeah? Okay. This is the probability that given the true class is negative, you predict as negative, right? Okay, so this is your specificity. So you're going by the column here. Now, so your PPV is basically going by the rows. So it's another type of conditioning, but you're conditioning on the predicted results. It goes like this, okay? So this is the probability that given the predicted is, you predict equals to plus. Okay, if you find that you get a plus for your prediction, what is the probability that the true class is plus? Okay, so this is actually quite interesting because you are asking the you are kind of like reversing the conditioning event, right? So then you reverse this, so you will get A over A plus B. Okay, so this tells you how useful, how informative is your plus prediction, right? If you get a plus prediction, does it mean that it is the true class is plus? Okay, so and then you have your NPV, which is to predict equals to negative. So the true class is negative, right? So it's this row, yeah? So you will get basically D over C plus D. Okay. And by the way, this column, so this cell here, this is a true positive, right? Yeah, when it is plus, you predict as plus. That's a true positive. So when it is a negative, you predict as negative. So this is also this is a true negative. Okay, and this one is a false positive, right? Yeah, false positive because the true class is negative, but you predict as positive, so it's false, right? So this one is a false negative. Okay. So false negative meaning that the true class is plus, but you predict as minus, right? You say that there's nothing, so it's a false negative. So depending on the context, sometimes false negative is more serious. Sometimes false positive is more serious, right? If you think of maybe a medical setting, right? False negative is probably more serious because a person has actually a disease, right? But the diagnosis is you have nothing, right? So the person doesn't receive medical treatment in the required time, so the person may actually die. Yeah. So a false negative may have serious medical implications. Okay. So for example, people with if if somebody has COVID, but the test result shows that this person is negative, then you have a false negative, and this person will go out and maybe interact with a lot of people, and so this person may actually spread the virus, right? So in this case also, your false negative is actually more serious compared to false negative is more serious. So compared to false positive, okay, let's say someone doesn't have COVID, but the result shows that this person has COVID. Of course, this person doesn't spread it because this person doesn't really have, but maybe psychologically the person may be affected. The person may be kind of like shunned by his colleagues and family. So that may also be bad from a personal point of view, all right? So you have to consider the context, yeah. Sometimes whether which type of errors is actually more serious, okay? So you have all these things, and then if you read the literature, they have got some additional other metrics, like sometimes they report something called the F1 score. The F1 score will basically be equal to the following. It's 1 over sensitivity plus the PPV divided by 2, right? So this is the harmonic mean. Okay, it's a harmonic mean of sensitivity and PPV. Okay. So if you want to emphasize on these two metrics, maybe perhaps you can use an F1 score. Otherwise, maybe sensitivity and specificity separately. Okay. There's also another metric called, very commonly used metric, which is called the area under curve. All right, area under the curve. So which basically looks like this. So this is your 1 minus specificity, and this is your sensitivity, all right? So it will go from 0 to 1, 0 to 1, right? Now, remember when you make decision, right? So let's say if you have two distributions like this for your classes. So let's say this is the red, this one is the blue. So you can actually consider multiple cutoffs, right? You can cut off you can use different decision cutoffs. So maybe you can cut off one here. So you can space out, right? You can space equally. Okay, use this cutoff. And for each cutoff, right, you can generate sensitivity and specificity, right? Because at each cutoff, you can generate a classification matrix like this, and then you can report your sensitivity and specificity, okay, and so on and so forth. So you can basically have a table. Basically have a table where this column is your cutoff. And start with 0.1. So you can start with 0.01, 0.02, whatever, right? Until 0.99. And then here you will have your sensitivity and specificity, right? So you can make the table like this, and then you can plot this graph, okay? So then you will have all these pairs of values which you can plot onto the graph here. So generally, what happens is that it will climb like this, like a step function. Okay, right. So this so for this graph, the area under the curve. So this graph, by the way, is called an ROC curve. ROC stands for something like this: receiving of sorry, a receiver. It has a weird kind of name. I think it's called receiver.
Receiver operating characteristic, I think.
Yeah, that's right. Receiver operating characteristic curve. ROC curve. Okay, this is ROC. Not sure why the person invented such a complicated name for such a simple graph, but I guess it gets attention, right? Okay, it's just a, if you just say it's a graph of sensitivity against the complement of specificity, then people don't pay attention. But you call it something like this, then people think it's sophisticated, right? So anyway, it's just some curve like this. Yeah, right. When the name is complicated, not so easy to remember. So that's why people just call ROC curve, ROC, yeah, ROC. Now, a good classifier, right? For a random guess, the ROC curve will behave like this. It will be like if you have a random guess, right? Your sensitivity will match the specificity at the y equals to x line, okay? So a good classifier usually will go to the space where it's above this line, okay? And what happens is that they overall they will classify the overall performance by calculating the area under the curve here. So it's called AUC. Okay, just area under the curve. So then they basically compare different classifiers by their AUC, right? The AUC is basically a kind of measure that integrates sensitivity and specificity. Okay, because just now if you have this data, right? So you're going to look at sensitivity and specificity kind of like separately, right? So when you look at it separately, maybe sometimes a little bit hard to decide. So then people kind of like say, okay, why don't I integrate them both? So the idea is to calculate the area under the curve. The area under the curve is basically some kind of function of sensitivity and specificity, right? Okay, because like for example, if you have a rectangle like this, then basically it's just your sensitivity multiplied by 1 minus specificity, okay? So these are basically the common metrics that people use. Although there are actually more metrics, right? These are just the common ones. Whether it's suitable or not for your study depends on the context, right? But so far, these are the commonly used ones. In some studies, you might actually may have a natural context whereby the sensitivity is the most important thing that the classifier should have, right? Like for example, you want to detect some very dangerous class, right? And if you are not able to detect that class, then there's going to be big trouble. So then you want your method to be very sensitive, right? So in that case, your sensitivity becomes the overdriving metric, okay, rather than your AUC, right? So this is basically the setup, right, for the metrics, okay. Right. Okay. Now, once we are settled with the metrics, then we will say something about how to properly evaluate a classifier. Okay. Okay. So when you have a data, okay. So these are your class labels. So then you have your variables, yeah. So these are your variables. Okay. So your class label may be, let's say a binary class, you may have something like this. Okay, so it's already kind of like sorted, right? Okay, you sort them. Okay. The first thing is the following. So you are going to use not all of your samples, but only partially, only a partial random sample from your data set. Okay, you use it to train the classifier. Train here means basically it means you use it to estimate the parameters, okay, of the classifier. Okay, so basically you use the a random subset. So for example, let's say if you have n plus is 100, and this one n minus is 100. Then what happens is that maybe in the simplest case, you could consider something like this. You randomly split your n plus to 50, n minus to 50 for your training. So basically over here, you will have a training set. And then over here, you will have a test set. And of course, the labels here, they are randomized, yeah? They have to be randomized in order to avoid specific data structures influencing your classifier too much, right? So you have to randomize them, and when you randomize them, in order for it to be reproducible, you basically use the set seed. So you set a seed, then you put a number here. Okay. So after you have set the seed, you randomize. Basically, you will get the same kind of you will get the same sample again and again. This is because your random numbers are basically generated using a pseudo random number generator. If you have studied taken a course in computer intensive methods, then you know that the random numbers are generated from some linear models, and but then it can be done in such a way that they appear to be almost taken from a uniform distribution. Okay. So okay, so this is done. So basically, you will have a randomized set. So you train, you test, right? So the train. So when you have a model. So you have a model like this. 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 So you have a model They use plus and minus, yeah. Okay. So you may actually estimate the, maybe this is the decision boundary, right? And then for the test, right? So basically the test will, so you have this, so this is your model. Of course, I'm just sketching this in 2 dimensions so that it is easy to visualize, but in fact, it lies in the multi-dimensional space, right? In generally, you will have more than two variables, right? Okay, so your decision boundary will be some boundary in an abstract space. Okay, so now your test sample will go in here. Okay, so maybe let me clear some space here just to sketch out. Right, I'm just reproducing this diagram up there. Okay. So I estimated the curve like this. All right. Now, so your test sample now comes. Okay. So your test sample, again, you map back to, so your test sample are the ones that you didn't use to estimate this line, right? So now it's an unseen sample, right? So the test sample may be going out like this. The green ones. Okay. And then all right. Okay. So then basically then you check whether the test samples they are inside the decision boundary that classifies it to be red, right? And so on, right? So from here you will be able to get a classification matrix. This one is for the test samples. So this is a plus minus plus minus. So this is a predicted. Okay, this is the observed, right? For the test sample. Okay. So in this way, you basically avoid overfitting, right? Okay. You can avoid overfitting if you set out one set of your data to be used as a test sample, right? So your test sample basically, you basically use the test sample to determine the performance, right? To get a better feel of the performance of the training sample. Okay, so rather than use the training sample to do the prediction. Okay, now in a related sense, so that you will come across certain terms called okay, you'll come across a term called cross-validation. Okay, so it will be something like called, let's say, k-fold cross-validation. Okay, so this k-fold cross-validation is basically just it basically does multiple rounds of this kinds of training and testing. Okay, so maybe let me sketch it out. K-fold cross-validation. K4 cross-validation can give you some idea, provide some idea about variability, right? Performance variability. Performance variance of a classifier. Your classifier definitely will have some performance variance, right? So how do you get this idea, right? You can't get the idea by just using a single test sample. So you need to use multiple test samples. So how do you do that? Okay. So basically, this is the data set just now. So you have your plus, your minus. Okay, so let's say you do a twofold cross-validation. A twofold cross-validation basically means you randomly partition, yeah, your data here into 2 layers. 2 layers, right? This is randomized already. Okay. So you randomize, then you, let's say if this is 100, so if this is 100, this is 100, that means this layer is 50, this layer is 50, right? Okay, you basically randomize, right? And then you cut at this point, right? Okay. So then, so this is plus. All right. So then you will take this layer. So this is layer 1, yeah, L1. So you take this layer to train your model. Okay, you take this layer to train your model, and you take the other layer, right? So this layer, you use it to predict as the test. Okay. After you're done with this, right, you swap. Okay. So you use the L1 layer to train. Then you predict L2. Then you reverse it. You take L2 layer to train, and then you predict L1. Okay. So this is a twofold cross-validation. When you do so, you will be able to have a table like this. So this will be a layer 1 used for testing, a training set. Sorry, test sample. Layer 2 used for test sample. So you can have your sensitivity, specificity, accuracy, or whatever. Okay. Maybe F1, whatever, right? Maybe also AOC, okay? So then because you got 2 layers here, so you can calculate the variance, yeah? Okay, you can calculate its standard deviation. So for this, so then you will be able to find the mean sensitivity plus minus 1 standard. You can find the plus minus 1. In this case, maybe if you want to, you can find the standard error, which is basically the SD over the square root of the number of layers. Okay. Right. So this will give you some idea about the variation, right, of your sensitivity, right? So previously you saw that it's just one number, right? Because you only use one data set to test. But now you can have multiple data sets to test. So you will have a mean, and then you will have the some measure of variability. Okay. This is one way to do it. The other way to do it is people basically report the worst result. Okay. So you got many layers, right? So you got many layers, 1 layer here, 1 layer here, and so on. So worst in maybe in a certain sense, maybe with respect to a particular metric, right? So for example, it will report the layer with the worst results, okay? Rather than taking the average. Okay, so but then sometimes basically what people do is since this is easily reported, so people report this and they also report the worst, for example, sensitivity. Okay, just to give people some idea that a lower bound, right, gives people some idea about the lower bound performance of this method, which is important because it's important to know like how bad your model can perform. Okay, some people like to play tricks. They, instead of giving the worst sensitivity, they give the best. This is totally useless. Of course, in the best situation, your model will maybe predict almost 100%, right? But we're not really interested in that. We want to know what is the lower bound of our performance, right? Because if the lower bound of our performance is already very high, then we can be very confident with our method, right? On the other hand, even if your mean is actually pretty good, but it can suffer from some very bad worst case scenario, then perhaps your classifier may be a bit dangerous to be used in real life, right? Because who knows, it might actually meet this really bad scenario from a future sample. Okay, so this is twofold cross validation. So basically, instead of twofold, you can basically generalize to k-fold. Yeah. Okay, so k-fold. So basically, k-fold will be you basically just slice the data to 10 layers. Right? Okay, slice to 10 layers. You will use, so for example, let's say it's 10-fold cross validation. You will retain, let's say you retain the fold 1, layer 1 for testing. Then layer 2 until layer 10 will be used for training, right? And after you are done with this, you use L2 for testing, L3 for testing, right? So if you have 10-fold cross validation, your performance metric here will have layer 1, layer 2, layer 3 until layer 10, right? So then it allows a better estimation of your standard error of your metric, the mean metric, okay? All right, so of course, if you take a large fold, then it is going to give you better estimates here. However, sometimes whether you can take 10-fold or not, I mean, there are all kinds of recommendations, so you shouldn't just blindly believe any magic number. There's no magic number here, yeah. Whether you choose k to be 5, choose k equal to 2, choose k equals to 10, ultimately depends on the data that you have, okay? So, for example, if let's say I give you a scenario, suppose you have n1 equals to 50, okay, sorry, plus n minus equals to 100, right? So if you do 10-fold cross validation, right? So what is the size of your test set for any layer? What would it be? Anyone?
10.
10, right? So 10, 10. Okay. Now, so you are basically just going to do a classification matrix like this, where this is the true plus this is the true. It's a predicted, right? Plus minus. So your true one only have 10, you know. Okay. Your contingency table only is playing with 20 numbers here. So even if you get something like this, so if you estimate the accuracy, it will be 17 out of 20. Will be looks quite high, right? It's like 0.85. Okay. However, since is actually not a lot, right? So basically your estimate here is also subject to quite large variation, okay? So in fact, in this case, maybe if you do tenfold, right, the estimate here are a bit, maybe a bit weak, I would say. I would suggest that your in one of these folds, right, you would have something that is more than 20 for each class, at least, so that your estimate here will be a bit better, right? Of course, the more you have, the better, but ultimately this depends on your available samples, right? So like for example, you only have 100, so if you're going to take 20, right? So maybe you can only do 5-fold. Okay, 5-fold, you will have 1-fold being 20, right? This 20, right? Okay. So you may need to do some kind of math to decide how many fold you want to do. Okay. Sometimes it's not that you don't want to do 10-fold or 20-fold. Some people can even do 20-fold, you know. But there's no point, right? Let's say you do 20-fold here. What will happen? This data you do 20-fold. 1-fold is what? 5, right? 5 only. So you got 5, you got a contingency table like this. I don't think you can estimate sensitivity, specificity, or even your accuracy to any reliable degree. Okay, so basically you set, if you set it too much, too high, right, the fold also useless. Okay. Okay, so this is to let you have this idea, cross-validation. Of course, you don't really have to write the program to do this kind of like, you know, layering, and then of course you're welcome to write your own script to do it. It's not that hard to write, okay? Not that hard to program, but it's just a bit tedious. And nowadays, all this, a lot of the RR packages, they already, a lot of these classifiers, right? They already have an integrated cross-validation function. So you just need to call out that argument, says, yes, I want to do cross-validation, and it will be done for you, right? So nowadays, very convenient, right? You don't have to, most likely you won't need to write your own cross-validation program, unless you are developing, like for example, new classifiers, right? You're developing new methods, then of course there will be no other people who have done this before, and therefore you will need to do your own cross-validation, right? But actually for routine work, very likely you will just need to check, you know, what argument that you need to call out in order to do cross-validation, right? Okay, so it's quite convenient. So it's also a good idea to have, yeah, cross-validation, because it will allow you to more reliably assess the generalizability of your classifiers for future samples. Okay. So this is for cross-validation. The other one is there's also a related method that uses a method called leave one out. Which is really a very old method that sometimes it is used. Leave one out, just to let you know. So leave one out basically is just like this. If you have 100, so 100, right? So basically I will use all, so there are 200, all 199 samples to train, and then a single one to predict. Okay, so then I will repeat this. In this case, for each one, so I repeat 200 times. Okay, so you have to build the model 200 times, and then train 200 times, right, with the sample that's left out. Okay, so this will be computationally intensive, And it depending on how fast your algorithm is, right, for running each classifier. This can take a bit of time, okay, if you decide to do this leave one out method. But I think this leave one out method is basically some method that people tried a long time ago before cross-validation. Okay, so basically I think cross-validation may be you just use cross-validation, I think it's enough. But just to keep this idea around, right? Okay, leave one out method.
Hello, doctor.
Okay, did somebody say something?
Wing Fong here.
Hi.
Good question. So regarding the leave one sample out, so if you are on rebuilding the model, right? So you got like, for example, 100 models, and then you use like one extra points to validate the model. So basically you are not validating the model that you develop, right? Because there's like 100 types of models.
Yeah, right. So, well, it basically is validating the, it's more like validating a particular methodology. Because at the end, right, you still have to, like, for example, even if you do cross-validation, okay? So you have your, so you have cross-validation, basically is like you have a classifier, right? So you basically use some, let me see. So, okay, so you basically have a training sample. So you get training sample 1, training sample 2, training sample 3, right? And test sample 1, test sample 2, test sample 3, so maybe test sample K or K4, right? And then you get some performance metrics for each of these test samples. Basically you are using different training samples, right, to get this, okay? So then basically then you will have some general idea about the performance variability. And even here, right, even you've got the K layers, every time you run it, the result will change because all these layers, right, they are randomized, isn't it? You take a random sample from your from your whole data, right, to become the training set, right? So basically when you do this thing here, it's more like you are kind of like validating a particular classifier, okay? So in order to deploy that model, you will still, in order to deploy a particular model, right, you will still need to settle to let's say so basically you have your entire data set here, right? So after that, you will basically train the model. You will train your classifier with the entire data set, okay? And then for this, you have the future. The future is unseen, okay? So then you will basically have your faith in this model because you have already evaluated it using cross-validation, right? So you have some idea about its variability. And therefore, finally, when you deploy, you decide which one to deploy, right? So use all the data that you have to train it. And then that's it, right? Because remember, your evaluation was done on the cross-validation, right? It's not done fully on the entire data set, okay? So So that's a difference between this and the example that I used just now, right? You just fully train the model and you go, okay? Because that one you never really evaluated it using this approach, okay? So you would basically just train the whole model. Train the model with the whole data set, and then these will be the things that you haven't seen before, okay, in the future. Then, of course, you can predict and then look at the result and then see, you can use it to update this particular model. So in your case, the leave one out, right? So basically leave one out is also kind of like giving you some kind of idea, right, about the variability, right, in the performance. Okay, so basically over here, if you leave one out, you predict, right? So you will get a whole bunch of predictions, like yeah, so you have 200 predictions, right, in this case. So yeah, does that answer your question?
So it's more like a check on the variability of the data. So
yeah. It's more like a way to check how stable is your classifier. If your classifier is very unstable, right? So it will do very badly in the leave one out. That means even if I train with the bulk of the data, I still predict it like with some variation, right? So then if that's the case, then you have to be careful with your model. Like for example, over here, right? If you don't want to use a K4 cross validation, you just use leave one out, right? The leave one out error, you can basically just look at the error lah. Okay, leave one out error will be the number of misclassifications, okay, the percentage. So leave one out error, let's say you got classifier 1, 2, 3, 4, 5. Let's say you got 5 classifiers. You want to decide which one to deploy, right, using the full data. Then you can look at the leave one out error. Okay, so let's say this error is 5%. This one is 20%. This one is 6%. This one maybe 8%. This one maybe 12%. Okay, so this one is telling you the amount of, it gives you some idea about their variability. Okay. If it's 20%, you probably will feel not so comfortable with this method because it's and at the same time, I don't know, some people will like to go for the minimum. Okay, they evaluate this. Let's say if they use leave one out as a quick method, they decide maybe they want to use 5. They take the minimum. I have a different philosophy here. My philosophy here is actually there's no magic formula to decide here, but you have to have some way of reasoning. I would say I wouldn't pick the one that is number 1. I will pick the number 2. I'll pick the number 2. So in this case, right, I will probably pick the method with 6%. Well, do you want to know the reason?
Yeah.
This one is I will say is called the number 2 principle. You know, people always like to focus on the number 1, right? Yeah, number 1, number 1, number 1. Okay. Actually, number 2, number 3, and number 4, they have their own strength, you know. Number 2, number 3, number 4, they are not always at the top, but they probably in the long run they probably kind of like first thing, because they are not number one. So first thing, it cannot overfit already. The number one always has a danger of overfitting. That one you have to be always be on guard, because remember when you do machine learning work, right? Most of the time your samples are observational data. So observational data, you don't know the bias. This is an admitted fact. Data is collected by some process that you have no control over, usually for the data miner. So you must always consider the possibility that your sample is biased. So therefore, when you choose classifiers, right? Although of course you can think of it as a mathematical problem or optimization and all that, but I would say if you pick number 2 or even number 3, that is kind of like understanding that guarding against the bias, which you are not able to quantify, because you know you are assuming that the bias may be negligible or something like that. So that allows you to because if your bias is a lot, then basically you're working with rubbish, right? Because if your data is totally biased, no point, right? Because it won't generalize very well. Okay, so you have to kind of like assume sort of that yes, there's bias, but maybe it's not that serious. Okay, but who knows, right? So my idea of pick the number 2 is in that way you can avoid overfitting, and in the event that there's no overfitting, right? In the event that your data is really you know, unbiased, more or less unbiased, then well, yes, of course, you kind of like lose out, right? But hey, you're number 2, right? You're not losing out a lot, isn't it? Okay, so that's my idea. You will not find it in the book. The books don't talk about these things. It's my kind of my own way of understanding how the bias comes in, and you know, so I mean, this is my own. If you ask me to pick, right, for real life, this is probably what I'm going to do.
But Doctor, to be honest, it's quite difficult to implement this kind of judgment in the industry. So basically, I work for the bank, and in the bank, they most of the time, for example, there's the 2% and the 5%. So most of the time they will go for the 2% because it's black and white, and because it's, you know, by looking at it, this is the evidence that this is the best model. But I mean, rarely people will understand that, oh, this is the number 2 principle. And yeah, so for example, in a very common case I see is the linear regression model. So where people always try to fit it to up to, like, you know, like a 98% just the R square and stuff like that, and then they don't accept a model which has like maybe 88 or 90% just the R square. Yeah, so
that's right. I think this is a problem with overemphasis on mathematical optimization. You know, because a lot of people who work in this area, they are very mathematical. But if you have worked with data for quite some time, then you will start to treat this optimization things as merely a kind of means to an end. You should not treat them as some kind of gospel truth or something like that, because you know, it's just a way to estimate parameters in some, like for example, you use all this optimization method is basically to allow you to get some estimates, right, of the parameters. That's fair enough. But beyond that, yeah, but I understand that, right? Because psychologically, it's not easy to justify this thing, because people, even in maths, right? Like people always look at maximum, minimum, that kind of thing, right? They don't go for number 2, number 3. So I think that has a lot of influence on how people actually think. And of course, you're right. You know, banks and all that being like you know, it's a kind of like a risk adverse.
The business-minded person will actually more. It's harder to convince them to take a second best option.
So yeah, because they will say that why, but that's precisely because they do not understand that the problem.
The technical details that is underlying.
Yeah,
it, yeah.
Yeah, I mean, especially true when the accountants come in and do the models.
The audit.
Yeah, because they are too much into the like everything is organized by numbers, which is actually wrong. There's a lot of variability in the data. Even like sometimes you got data errors creep in. Who knows? So you optimize and you take the best model. You're basically optimizing for the errors, you know. So yeah, that's why I know it's difficult if you are working with teams like that. That's why this kind of thing. But if you're doing things on your own, right? I don't know if you develop your own models for your own work. This is something that is worth considering. Yeah, that you try to maybe take the number 2 or even number 3. You like number 3.
Just don't report the number one. It will be fine, I guess. Following from case. I mean, it's just a matter of reporting whether did you do your number 1 or number 2 or number 3. You just report the one that you think is the best, right?
You start to worry when the audit comes in.
Because it's safe, you see. When you do the max thing, it is like safe, you see. And people usually in the industry, they play safe, you see. That's why, but then I think that there's more scope. Let's say if you're doing R&D, so then probably like since the R&D, right? So you could try out different ideas. But really in the industry, sometimes people are a bit. It's more like to.
Depends on the boss.
Again, I guess it depends also on the boss whether they understand it. Yeah, that's I think.
Yeah. The other thing is always they are seeking for improvement of the models. So it's like they would expect the model can be improved. It's like something like KPI.
Yeah, but to be realistic, that's not possible.
It depends on the data actually.
It depends on the features that you're using. Yeah, so it's not, and maybe like up to a certain point, there's no more point to try to improve the model because
the effort spent is quite long compared the effort and also cost spending.
Yeah. So it does not commensurate with the effort. You may be able to improve it by maybe slightly, but usually it's like this. The models, right? They early stage from crude to something mid sophisticated. Then you see quite a lot of gain. Then after that, you try to push it a bit, right? It's like you have an orange. You make the first press, and then you press second round to get more juice. And I think the second press already is a bit like you need to press very
lesser, yeah, pressing very hard.
So some people like to do this, right? Sometimes they because it's easy, right? The orange is in front of you, so you just keep pressing it, right? So
it's like torturing the data to get the scene true, but it's not true.
If you want to do something more meaningful, I think after the first press, you get something more or less pretty good. Just move on to another project. Yeah, I mean, like, at least that's what I would do. I wouldn't keep pressing for it because it takes a lot of effort. So I think, yeah. So that's some sharing. Yeah. Okay, so I don't know, like maybe for some kind of data sets, you could actually, test out this number 2 principle. Like you basically before you do this entire, there's one way to do it. So, but then again, it depends on an assumption. So it's like this. If you really want to test this principle, you have a data, right? You before you do the analysis, this is your entire data. Okay. Before you actually do it, you actually isolate this whole part. which is for your future data. Now, of course, and then you only use this part, right, for the training and testing, for evaluation, right, for different models, model 1, model 2, model 3, model 4, and so on. And then maybe you pick, so this is the top 1, number 2. So then you, from here, right, you can use this future data to kind of like evaluate who wins. Okay, this is one way to do it. So you have to kind of like reserve it. The only problem with this approach is that, again, it presupposes that this one future, when you isolate like that, this is actually kind of like approximating real future data, you know. All right, the future is here, so we don't know, right? If the future happens to be approximately equal to this part, then yes, yeah, then you will look like you are a genius. But if the real future data is something else, that this is not even close, like nothing here is close enough to the future, then again it will flop. Okay, that's why the question of bias here is really important, because if your sample here, right, is basically so let's say this real future data is somewhere like this, the distributions like that. If you have collected your evaluation data from, let's say, not representatively over it, but maybe just this corner, right? You will have a lot of data. Of course, you can have a lot of data, but you may have collected only for this corner of the entire data that's going to come from the future, like hypothetically. Then, of course, the model that you train, no matter what you do here, you use number 2 principle also, whatever, you will also fail with this part quite badly. Okay, so really the problem of bias here is something that we have no control over, especially for the data miner. Right? Yeah, this is something that people who believe that machine learning can solve all problems should be aware. Yeah, it is only as good as the data that you use to train it. All right. So perhaps you know, more experienced data miners, machine learning people, they usually start to pay more attention to how the data was collected and data features and things like that, rather than obsess over like algorithm optimization parameters, stuff like that. Because they know that those things will really no more matter because of this phenomenon, right? They are more focused on this data here being representative. And it's difficult, okay? Trying to make sure the data that goes in here is representative of the future process here is a difficult thing to do. Okay, but if you could do that, then yeah, okay, then maybe they will hit some kind of gold mine, right? Okay. Some comments here. If you like, keep pressing should go Kaggle. Yeah, sure. Yeah, that's why Kaggle, right? They have all these competitions. Yeah, so then they will compete to see who can come up with a machine learning algorithm that makes the best prediction, right? So unfortunately, I think it's cool to, that kind of competition is good for honing your programming skills. But I think from a conceptual point of view, it's like modeling. I think it may be modeling too much of the idiosyncrasies of the data. So in fact, that might actually give people some false sense of superiority, that they can do machine learning very well, and they can optimize this and that, and then they think that they will get get some some kind of super performing model. So that might be, but if you understand that, then maybe it's just, you know, it's good for training the technical aspects rather than, let's say, being a kind of a reflection of real world success. Okay, so yeah, so that's quite a good discussion. So you just have a bit like maybe some 10 minutes left. Initially, I wanted to say something about the shrinkage method for lasso, but maybe I'll just leave it for next week. But you can play with that. I think in the code, you might need to edit things a little bit because I think Jake pointed out to me, if you look at the code.
Yeah, but then I changed it in the way that like what you mentioned. So I just
Otherwise, it won't run, I think.
Yeah, it's too much of changing down there later on. So I just take your advice there. Yeah.
Yeah, because I forgot to copy one line of code. So let me see, where was that?
Should be right before CV1. There's something that you did over there. Yeah.
Okay, this one, right?
Yep. Because in between BC and CV1, the BC first column is actually ID.
Yeah, so I think there's this one. I left out this line of code, I think.
Yep.
Yeah, because the first column I think is the sample ID, so I kind of like removed it already because it's useless. Then over here, then this one is the first part is the data. So because then after you remove the first column, now becomes the class label. So then it uses the data and then the class label, and then this is a logistic regression. So then after that, it should be okay. Yeah. So add one line of code here. Okay, just remove.
And also, right, I think I'm not so sure if you're gonna show the histogram, because the last part of the histogram itself, you have this x limit scale is -15 to 15, but the value is actually from 0 to 1.
Oh, okay. Because, yeah, right, because I didn't, yeah. So this one is after you convert. If you didn't convert, then this will be okay. So this one you can change to 0, 1. Okay, because previously I didn't convert this. So it will just end up with the linear form, yeah. So the linear form will run between here. So yeah, so you can change this to basically 0, 1, and because then it's now a probability. Okay. Actually, you can also use. So this predictor is basically just predicting the. But actually, over here you can, if you don't want this line here, I think you can put something like type equals to response. I think it will give you the probability. Okay, so you can go and see something about predict. This predict is very useful. Once you have got a model, right? You put in the data here. So this data can be your training data. It can also be your test data, whatever, depending on what you want, right? So in this case, I'm just doing very, I mean, like I'm just using my training sample as for prediction. So then I do it like this, right? But if you have some test sample that is not used for training, you can also put it here. Okay. So this lasso is basically a very useful way to do feature selection, whereby it so it's like doing regression with the regression coefficients, right? But it has a way to actually identify those coefficients and directly shrink them to 0. Okay, directly make the coefficient to 0 rather than estimating them. So when you make the coefficient to 0, right, then that variable becomes unimportant. So basically, it will get filtered out. Right? So then it's a way to do feature selection as well. So this Lasso paper is considered one of the main developments in regression methods, yeah, for so-called modern regression methods. You know all the regression methods that you learn in third year. I don't know if anyone has learned Lasso before, or its predecessor is called the ridge regression. Anybody learned this before?
I think it should be both, right, ridge and lasso, the L1, L2 regularization.
Yeah, it's a related kind of method, but ridge regression came up first. Then only Lasso is a bit harder to do because its penalty is actually not is a L1 norm rather than an L2 norm. L2 norm is quadratic, so it's easy to do. But the L1 norm is absolute, so it's a bit harder. That's why it involved a bit of technical stuff, but then only it got solved. So this is considered. Anybody learned this before? Maybe you come across it anyhow.
Came across it, yes. Learned it wise. I only remember what's the usage. Doesn't remember about our formulas and something about the square and circle.
Yeah, basically, it's a very complicated piece of work. If you read you can read the original paper. It's very technical. But the general idea is it uses a kind of a shrinkage method. So you can read the notes that I gave there. Like it's just they basically just have some kind of penalty function where they do the estimation, right? They take that penalty function into consideration. Your ordinary least square doesn't have that penalty function. So yeah, so that's why you can use it for feature selection, you see, because it shrinks those coefficients to 0, and then you can eliminate those variables as features. In fact, this one gives pretty good result. You just directly put the Wisconsin breast cancer data into it. It does the feature selection for you, and you can see that the performance is pretty good, right, in terms of the graphical output. This is considered one of the major developments in regression methods. But even with Lasso, this is already, I think, maybe more than 20 years, maybe 20 plus years, close to 30 years maybe. So the more modern version of Lasso is called elastic net. Yeah. So I think this one can also implement elastic net. I think you basically just need to change alpha. Instead of 1, you change it to some value between 0 and 1. Okay, so it will then implement this so-called elastic net variable selection. Right? So you can try that. This is definitely a powerful tool for use in machine learning. Yeah, this is and this is basically developed by statisticians. Okay, the Lasso method is basically a method created by statisticians, so they kind of like it a lot. Okay, so at least we can use it in our work, yeah, for Lasso. Okay, so you play with this a little bit, and then maybe next week we'll talk more about some other models. So next week I'm going to talk about the tree, and then a bit about neural networks, right? Then yeah, maybe also cover, if we have time, we cover the naive Bayes also. So still have about maybe 3 methods, something like that should be done. Then after that, you can start to use these methods to work on the data set that you worked with before. Yeah. Okay. Some of the methods some data sets are better suited to certain methods. Like for example, the diabetes data will, because it's all 0, 1, right? That one is very obvious. That one, the decision tree will be very obvious choice, okay, compared to other methods. And so sometimes you will also see different data types suited to certain classifiers are stronger with respect to certain data types, right? So that one you can also find out when you do the analysis, okay? Okay, right, okay, so that's all for today. Attendance, okay, I'm going to open it later after this, and you just record it. I'm just going to open it until 10 o'clock, all right? So you just log in and then tick, all right? Okay, so are there any questions? Any more questions?
No, I think.
Johan wants to run already. Quickly says no.
No. No.
Okay, it's okay, just joking. Yeah, okay. Right, okay, so I'm going to stop recording now, and that's all for this week, okay? Please try to run the codes, all the R codes that I put up, at least try to run them to see what you get, okay? And try to reproduce the decision boundaries in the SVM. Right.
Okay, thank you, doctor.
Okay, thanks for listening. So I'm going to stop now.